Hi everyone, welcome back to Chem Story. Today, we're diving into how alkenes react with hydrogen gas. This reaction is called catalytic hydrogenation, and it plays a really important role in organic synthesis, especially when we want to turn a double bond into a single bond. So in this lesson, we'll break down how the reaction works, what kinds of catalysts are used, and why this reaction is so stereoselective. So what exactly is catalytic hydrogenation? It's a reaction that turns an alkene into an alkane by adding hydrogen gas, or H2, in the presence of a metal catalyst. Here's what happens. The pi bond in the alkene breaks, and two hydrogen atoms get added, one to each carbon. Now, here's something important. This reaction isn't about where the hydrogens go, so there's no regioselectivity to worry about. But it is stereoselective, because both hydrogens add to the same face of the double bond. That's what we call syn addition, and we'll come back to that in just a bit. But first, let's see how this works at the molecular level. Let's walk through how the mechanism works. First, hydrogen gas gets absorbed onto the surface of a metal catalyst, something like palladium or platinum. Then the alkene also binds to that same surface. So now, both the hydrogens and the alkene are sitting side by side on the metal. That sets up the perfect situation, where the two hydrogens can be added from the same side. And that's why catalytic hydrogenation always gives syn addition, because both hydrogens come in together from the metal surface. There's another benefit too. These metal catalysts help weaken the HH bond, which lowers the activation energy and speeds up the reaction. Now let's talk about the catalysts. The most commonly used ones in this reaction are called heterogeneous catalysts. That just means they don't dissolve in the reaction mixture. They stay solid, but still participate in the reaction on their surface. And that makes things really convenient, because once the reaction's done, you can easily separate the catalyst, usually just by filtration. Some common examples are palladium on carbon, platinum dioxide, also known as Adam's catalyst, and Raney nickel. Now let's take a look at homogeneous catalysts. These are a bit different. Homogeneous catalysts are actually dissolved in the reaction solvent, and that makes them especially useful for asymmetric hydrogenation, since the reaction can happen more evenly throughout the solution. What's really powerful here is that we can fine-tune the stereoselectivity by attaching different ligands to the metal center. That gives chemists precise control over how the hydrogen atoms are added. Famous examples include Wilkinson's catalyst, based on rhodium, and the Noyori catalyst, which uses ruthenium. Alright, now let's talk about stereochemistry. As we've seen, catalytic hydrogenation gives us syn addition, meaning both hydrogens add to the same side of the double bond. But here's something to keep in mind. In a typical hydrogenation, the alkene binds to the metal surface, and since the molecule is planar, hydrogen can approach from either face, the top, or the bottom. So if the reaction creates a new chiral center, you often end up with equal amounts of both enantiomers, which means the product is a racemic mixture. That said, the steric environment around the double bond can shift the balance. If one side is more hindered, the other side might be easier to approach, and that can affect the stereochemical outcome. Let's look at an example, alpha-pinene. This molecule has a double bond inside a rigid bicyclic structure. And if you check out its 3D shape, you'll see that the top face is pretty bulky, thanks to another ring and two methyl groups. So when alpha-pinene binds to the catalyst, like palladium on carbon, it's much easier for it to approach through the bottom face, where there's less steric hindrance. As a result, the hydrogens add from the bottom, and you still get syn addition, just from the more accessible side. It's a great example of how a molecule's overall shape can influence both stereoselectivity and the final structure of the product. It's not just about where the double bond is, it's about what the rest of the molecule is doing too. Alright, let's wrap things up by talking about how the structure of an alkene affects its reactivity. In general, less substituted alkenes react more easily. That's because bulky groups near the double bond create steric hindrance, which makes it harder for the alkene to reach the catalyst surface. So if you follow the trend, monosubstituted alkenes hydrogenate the fastest, followed by disubstituted and trisubstituted ones. And tetrasubstituted alkenes are the slowest. Sometimes they don't react at all under standard conditions. It's a good reminder that structure really matters, even in a reaction that seems as simple as catalytic hydrogenation. Thanks so much for watching, and I'll see you in the next Chem Story video.